I want you to try and imagine a thought experiment for a second. Imagine you've been tasked with mapping out every single road on Earth. Not just the interstate highways, but, every single dirt path in the rural mountains,
Right.
every back alley in dense cities, every private driveway on the planet.
Which is, that's a completely unfathomable cartography project on its own.
It is, but it gets harder. Now, add real-time traffic to that map. Every car, every delivery truck, every bicycle in motion. And then, and this is the kicker, overlay the weather patterns.
Oh, wow.
Yeah, wind speed, rain, temperature affecting every single millimeter of those roads, all updating simultaneously. It sounds mathematically impossible, but when you look at the raw data required to map the human brain, you realize that mapping the brain is actually exponentially harder than that global real-time traffic map.
It really is. The sheer scale of the biological hardware inside our own heads, it just breaks most of our conventional models for complexity. Like, we default to thinking of the brain as this neat, highly organized computer, right?
Yeah, exactly.
But the reality of reverse engineering that tissue is infinitely more chaotic than that.
Well, welcome to the deep dive. Today, we are going on a mission. We are exploring the absolute bleeding edge of how humans are attempting to reverse engineer intelligence.
It's a fascinating topic.
It really is. We've pulled together this amazing stack of transcripts and reports from the Orthogonal Research and Education Laboratory for you. And we are looking at everything from the moonshot quest to digitally emulate biological brains to training AI models to actually resurrect the minds of early cybernetics pioneers.
Yeah, that part is wild.
And finally, how you and I are supposed to adapt to this exploding complexity in our everyday lives. Okay, let's unpack this, starting with the physical hardware itself.
Right. So if we want to understand the origins of intelligence, the physical structure generating it is, well, it's the necessary ground floor.
Yeah.
In the sources you mentioned, there's this really comprehensive breakdown of the state of brain emulation report. And it outlines what it actually takes to digitally emulate a biological brain. It categorizes the problem into 3 sequential, incredibly difficult capabilities.
Because, you can't just take a high-resolution photograph and call it a day, right?
Far from it. So first, you need the ability to record neural activity. That means tracking the actual electrical firing of the neurons in real time.
Okay, that makes sense.
Second, you need connectomics, and that is the physical reconstruction of the brain's wiring diagram. You are mapping which neuron connects to which across billions of pathways.
Billions.
Yeah. And then third, you have to take that immense data set and digitally model those interactions in a way that actually simulates the biological function.
And the scale of this progression is just mind-blowing to me. Like, the sources track this, starting from the nematode worm, C. elegans. That tiny worm has exactly 302 neurons.
Which makes it a very tractable starting point for early researchers. It's manageable.
Right. But then you move up to Drosophila fruit flies, sitting at hundreds of thousands of neurons. And then you arrive at the human brain, which is hovering around, 86 billion neurons?
Yeah, roughly 86 billion. And watching how the cost and data requirements scale with that biological leap, it reveals the real bottleneck here. The sources highlight that mapping the original C. elegans connectome cost an estimated $16,500 per reconstructed neuron.
Which is an astronomical price tag for mapping a microscopic worm.
It really is. But thanks to better electron microscopy and AI tracing algorithms, that cost has dropped significantly. We're down to about $100 per neuron for something like a larval zebrafish.
Okay, so that's progress.
It is, but the financial cost isn't even the primary issue anymore. The data storage requirement is where the physics of our current technology just start to break down. To map just a 1 millimeter cube of a mouse brain at a 10 nanometer resolution, you generate 1 exabyte of data.
Wait, I need to pause on that. 1 exabyte for a speck of tissue?
Yes, 1 single exabyte.
It means the bottleneck isn't even neurobiology anymore. It's pure data center physics. Like, where do you even put the servers for that?
Exactly. And that 10 nanometer resolution, it's non-negotiable too.
Why is that?
Because if you zoom out any further, you miss the synaptic vesicles. Those are the tiny packets of chemicals that neurons use to communicate. If you miss the vesicles, you miss the chemical weight of the connection, rendering the entire map basically useless.
Oh, wow.
So you are locked into that massive data requirement. And if you scale that up to a whole human brain, you are looking at up to 1.4 zettabytes of data.
I'm looking at this and thinking, isn't that kind of a massive waste of resources? Because the brain isn't just fixed wires. The sources mention that receptor proteins in our synapses are constantly remodeling over time, right?
Yeah, it's true.
Like they change in density, they shift locations, cells alter their own membranes based on whatever you learned that morning. A static map seems completely useless for a dynamic system that rewires itself every time you form a memory.
I mean, it provides the indispensable base architecture. But you are hitting on the exact wall neuroscientists call the snapshot problem.
The snapshot problem.
Right. Taking a static 1.4 zettabyte photo of the brain is incredibly limited because structure without function eventually hits a dead end in understanding cognition.
It's like trying to understand the rules of basketball by looking at a single photograph of a player suspended in midair. You completely miss the motion, the physics, the objective of the game.
That is a perfect analogy. And that limitation is forcing the field to pivot toward what they call embodied models.
Okay, what does that look like?
Well, researchers take these digital brain emulations and embed them into virtual environments or physical robotic chassis. The digital brain actually has to process continuous, chaotic sensory data and generate physical output behaviors.
So it's actually interacting.
Yes, because intelligence requires friction with an environment. It's an active process, not a frozen diagram.
But here is the real leap, I think. If taking a static snapshot hits a dead end because the brain is constantly remodeling itself, we can't just map the final product. We actually have to figure out how the brain builds itself in real time.
Exactly. And this represents a massive paradigm shift in the sources, moving from static cartography to developmental AI.
Right. They introduced this framework called ConGA, that's connectome generating AI.
Yes.
The way I visualize the difference is like trying to reverse engineer a complex, multi-tiered wedding cake. The static mapping approach is like writing down the exact 3D coordinate of every single crumb and molecule of frosting.
Which would take forever.
Right. But ConGA is basically saying stop mapping the crumbs, just figure out the recipe and bake it yourself.
That encapsulates the goal perfectly. Researchers are attempting to write the genetic seed that grows the digital brain. Biologically speaking, they execute this using models called neural cellular automata, or NCAs.
Okay, and
Think of a grid where each cell only knows what its immediate neighbors are doing. By passing really simple rules back and forth, they generate incredibly complex coordinated structures.
And they pair those structural rules with biological gene expression, right? Because the sources mention transcriptomics.
Yeah, transcriptomics. That's the study of RNA transcripts, the chemical instructions being read inside a cell at any given moment.
Okay.
So researchers match the simulated cells in the NCA with actual biological gene expression data. They use latent variables they call barcodes to decode how the brain wires itself.
Let's break down that barcode concept a bit because it sounds kind of abstract.
Sure. Think of these barcodes like ZIP codes on a biological envelope. The neural cellular automata reads the genetic ZIP code, the unique chemical signature in a specific cell, and based on that code, it knows exactly which neighboring neuron it needs to reach out and connect with.
So it's building the broader neighborhood of the brain.
Exactly. It's an AI learning the local genetic rules that drive macro-level wiring.
There is a massive biological quirk here that the sources highlight, though, which makes this developmental approach so treacherous. This whole model struggles because the transcription factors, the chemical foreman directing this cellular construction site, are what biologists call transient.
Yes. They do their highly specific developmental job, like, say, guiding an axon across the brain to its target. And then they vanish entirely from the biological record.
So by the time you take your zettabyte snapshot of the adult brain, the very instructions that built the architecture are completely gone.
Poof, gone.
The scaffolding of the building was dismantled and burned before you even brought your camera out.
It really exposes the profound messiness of reverse engineering biological wetware. Evolution is a hacker, It doesn't leave clean documentation behind.
No, it definitely doesn't.
And recognizing how fragile and transient biology can be explains why a separate faction of researchers in our sources takes a completely different route. If simulating the biological wetware is just too chaotic, they suggest abandoning the biology altogether to emulate the pure logic of intelligence.
This brings us to one of the most fascinating projects in the transcripts. They are building AI agents trained to essentially resurrect the minds of the early pioneers of systems theory. It's called the Ask a Cyberneticist project.
Yeah, they are leveraging large language models for historical synthesis. They digitize the notebooks, the personal letters, and the academic papers of foundational cybernetics figures.
People like W.R. Ashby, Warren McCulloch, and Heinz von Forster.
Exactly. And they fine-tune specific models on their distinct intellectual frameworks.
It's practically like holding a digital seance with the founders of cybernetics. And they feed a very specific concept into the Ashby model, which is his definition of variety.
Right. W.R. Ashby's concept of variety is a foundational pillar of systems theory. He defined it as a strict mathematical measure of complexity. Specifically, the total number of distinguishable states a system can exhibit.
The transcript uses a great simple example for this. A standard traffic light has 3 distinct states: red, yellow, and green. Therefore, it has a variety of 3.
It seems basic, right? But Ashby scaled that concept up to explain the survival of incredibly complex systems through his law of requisite variety.
Which is a huge concept.
Huge. The law states that in order to successfully regulate a system, the controller must have at least as much variety as many possible states and responses as the system it is attempting to regulate.
The famous phrasing is, only variety can destroy variety.
Exactly. It comes down to biological and systemic survival. If a chaotic environment throws 100 different unpredictable scenarios at an organism, well, that organism's regulatory system needs 100 different ways to process and respond to those scenarios.
Otherwise, it's in trouble.
Right. If its internal variety is lower than the environmental variety, the organism fails and dies.
Which leads directly into his concept of the ultrastable system. An ultrastable system has 2 distinct levels of feedback. The first is a primary feedback loop. That's for standard day-to-day conditions.
Like a thermostat.
Yeah, exactly. A thermostat turning on the heat when the room gets cold is a primary loop maintaining equilibrium.
But the real breakthrough in Ashby's thinking happens when the primary loop fails. When the system faces an environmental disturbance so extreme that the primary loop just can't handle it, a secondary loop kicks in.
Okay.
And the secondary loop relies on what Ashby called step functions.
Wait, hold on. A secondary loop that relies on step functions. What does a step function actually look like in practice?
It represents a discrete, sudden shift in the system's underlying parameters. If we stretch the thermostat analogy, a primary loop turns the dial to increase the heat. But if the house catches on fire, well, that's an extreme environmental disturbance.
Yeah, turning the dial does absolutely nothing.
Right. A step function means the thermostat physically reorganizes its own internal wiring to become a fire suppression system. It fundamentally swaps out its operational rules.
It doesn't just adjust the current strategy, it basically mutates into a new strategy entirely.
Ashby described it as a rigorous trial and error state shift. The system continuously, fundamentally reorganizes its internal parameters until it stumbles into an organization that can survive the new environmental chaos.
Okay, here's where that's really interesting. Because these AI models can simulate intellectual debates, if you ask the AI to compare these historical figures, how does Ashby's view of feedback actually differ from his contemporaries, like Warren McCulloch? Because they were working in the same room on the same broad problems in the 1940s and 50s.
Yeah, and training specialized AI agents on distinct data sets reveals that exact historical nuance. McCulloch approached feedback through a biological, neural, and highly goal-directed lens.
Okay, goal-directed.
He was fascinated by what feedback makes possible. How circular causality inside a neural network allows an organism to execute purposeful, intentional behavior in the world.
So he's really looking at the mechanics of purpose.
Right. While Ashby viewed feedback mathematically and abstractly, he wasn't concerned with biological purpose. For Ashby, feedback was strictly a mechanism for variety reduction and stability.
Interesting.
McCulloch was exploring what feedback allows an organism to do. Ashby was formalizing the mathematical laws of what feedback must do to prevent a system from collapsing.
It's almost the difference between a neurologist studying how a bird flies and a physicist studying the aerodynamic math of why it doesn't fall.
That's a great way to frame it.
So we spent a lot of time on theory here, mapping physical brains and modeling abstract cybernetic math. But the sources show what happens when these digital minds are finally taken out of the lab and set loose to act independently in the real world.
Yes, we are crossing the threshold from theoretical models to applied agentic systems.
There is a project highlighted in the transcripts called OpenClaw. It's an open source framework for agentic coding. Developers, specifically pointing to Lady Ada from Adafruit, are deploying it to execute autonomous firmware programming.
And agentic coding is a massive leap beyond simple autocomplete. You are giving an AI model a broader context window, short-term memory, and the execution permissions to write code, compile it, test for bugs, read the error logs, and then rewrite its own work entirely autonomously.
But the truly revealing experiment is when researchers force these agents to interact with each other. They use these frameworks to simulate group dynamics in open-source team chats.
Because observing multi-agent interactions exposes the limitations of default AI behavior.
Yeah, the sources note it was initially a complete failure of realism. The AI agents spoke in this highly robotic, perfectly polite serial loop.
Right.
Alice speaks, then Bob speaks, then Carol speaks. A perfectly symmetrical round-robin distribution of conversation that just looped infinitely.
Which bears absolutely no resemblance to how actual humans collaborate or communicate.
Not at all. To fix that unnatural looping, the developers introduced a probabilistic selection mechanism based on a new internal variable for each agent, which they called motivation.
I love this part. By weighting the mathematical probability of an agent speaking against their internal motivation parameter, this simulation broke the robotic loop.
Fix it.
It suddenly mirrored a realistic, messy human team dynamic. A highly motivated agent will dominate the chat, interrupting others and pushing the agenda, while an agent assigned a low motivation parameter might just lurk silently and barely chime in.
It mathematically forces the AI to mimic the reality of a modern Slack channel, where one person writes paragraphs and someone else just reacts with a thumbs-up emoji.
Exactly.
But they aren't just using agents to simulate chat rooms, they are using them for heavy scientific lifting, too. The sources detailed the Brain GPT project pioneered by Brad Love.
Yeah. BrainGPT is a highly specialized application. It's an AI model trained exclusively on the vast corpus of neuroscience papers, designed specifically to predict the outcomes of complex experimental designs.
But how does an AI reliably predict an experiment that hasn't even been run yet?
It relies on mathematical word embeddings in a high-dimensional vector space. When a human researcher does a standard keyword search, they are strictly bound by the vocabulary of their specific subfield. If you search for synaptic plasticity, you only get papers using those exact words.
So you are basically trapped in your own silo.
Exactly. But an agentic system like BrainGPT bypasses keywords entirely. It maps the underlying computational structure of the research.
Oh, I see.
It can look at a problem a researcher is having with tissue microstructure and realize that the computational math of that problem perfectly matches a solution already discovered in, say, fluid dynamics or astrophysics.
Wow.
It connects conceptual dots across entirely distinct disciplines that a human researcher would never even think to search for.
It's synthesizing knowledge across the entire universe of human data. But this brings us to a massive pressing issue. We are talking about data centers required to house zettabyte brain maps, digital connectomes grown from chemical ZIP codes, and autonomous coding agents predicting scientific breakthroughs across disciplines.
Yeah, it's a lot.
The natural question for you, listening to this right now, is how on earth are we supposed to keep up with this level of complexity?
It is arguably the defining cognitive crisis of our time.
Yeah.
And it is addressed head-on in the sources through the JoPro Year in Review update.
They highlight a phenomenon they call 21st century directionlessness. I think anyone working today understands exactly what that phrase means.
It diagnoses the baseline anxiety of the modern knowledge worker. People are rapidly adopting all these new AI tools. They're processing more information than ever before, yet they feel completely adrift.
Right.
They cannot see how their isolated daily tasks map onto a broader landscape that fundamentally shifts its architecture every few months.
I think about it this way. It's like we're trying to run state-of-the-art generative AI software on a 1950s television set. Our legacy institutions, our universities, our corporate hierarchies, our research labs, they were built for a completely different century.
They really were.
They were designed around slow, multi-year feedback cycles, highly rigid disciplinary boundaries, and predictable linear career paths.
And those 20th century structures shatter under the sheer weight of 21st century complexity. When fields of study collide at the velocity they are colliding today, isolated disciplinary pipelines fail to produce useful outcomes.
So the sources propose a specific solution to this institutional failure. They argue we need to cultivate a new kind of professional entirely, someone they refer to as a philosopher-builder.
Right. Philosopher-builder is a total rejection of the hyper-specialized technician. It describes an individual who doesn't merely execute narrow technical tasks, but someone who possesses the philosophical, ethical, and structural grounding to build coherence across those broken silos.
They're bridging the gaps.
Yes. They actively design the conditions for responsible innovation.
Because right now, structural responsibility is usually outsourced to, like, an ethics board totally detached from the lived reality of building the technology. It's treated as an afterthought or a compliance checklist.
Exactly. And the sources reference an ethnography of this modern workplace condition titled Something in the Way. It studies the friction of feeling professionally and cognitively adrift. Their core finding is that our approach to learning and professional development has to change entirely.
Okay.
Learning can no longer be a linear pipeline of memorizing static facts.
They argue it has to be trajectory aware. What does that actually mean in practice?
It means understanding the vector of your field, not just its current state. You can't just learn a specific coding language. You have to understand the computational trajectory of why that language was created and what will inevitably replace it.
That makes a lot of sense.
Learning must be highly contextual and embedded in real problems. You cannot teach AI alignment in a vacuum. A philosopher-builder has to be trained in the messy, interdisciplinary trenches, dealing with actual technological friction and human organizational failures, supported by adequate scaffolding.
So what does this all mean? We've covered an immense amount of ground today. We started by confronting the physical limits of mapping the human brain, staring down exabytes of data just to see the chemical connections.
Yep.
We explored how researchers are bypassing static maps by writing the genetic recipes to grow digital brains. We resurrected the mathematical logic of early cybernetics to understand how systems survive chaos. And ultimately, we arrived at the profound need for human philosopher-builders to navigate this rapidly shifting landscape we are creating.
It is a sweeping trajectory from the granular mechanics of biology to the philosophy of how we manage our own creations. And if I can leave you with one final practical thought to mull over, I want you to apply Ashby's law of requisite variety to your own life.
The law stating that a controller must have as much complexity as the system it regulates.
This is the real insight here. When you feel overwhelmed at work, when you experience that 21st century directionlessness, it is mathematically because your environment possesses more variety than your internal coping systems.
Oh, wow.
You literally do not have enough internal responses to handle the chaos being thrown at you. As global AI capabilities explode, the external world is gaining variety at an unprecedented rate.
Right.
Ashby's math proves that you cannot simply ignore the chaos. The ultimate imperative isn't just building artificial brains, it is figuring out how to use these tools to drastically upgrade your own internal complexity.
You physically have to upgrade your own variety to survive the environment. I love that framing. Because if you don't build out your own responses, you are going to be hopelessly lost trying to read a map of the Earth that changes every single second. Thank you for joining us on this deep dive. Keep asking questions, keep expanding your variety, and we will see you next time.